So we're very grateful to have him come and tell us about entropy power inequalities.
Thank you, Andrew. So it's a real pleasure and honor to be here. I don't travel very much these days, but I couldn't miss this celebration of Andrew's work. So in terms of what I'm going to talk about, I thought, I thought I would talk about the various themes that have emerged out of work that I first started thinking about with Andrew when I was first here at Yale around 2006. One of the things we did early on, Andrew was my mentor here, and having come from from studying with Yanis, who in his beautiful talk earlier this afternoon outlined the interactions between information theory and probability and how one can use information theory to illuminate probabilistic results. Andrew and I co-taught a course on information and probability in 2006, and as we were figuring out the things to teach, one of the things that we wanted to teach was the recently at that time discovered monotonicity of entropy in the central limit theorem. And while we were figuring out how to teach that, we realized there was a simpler way to prove that result, and that is the beginning of the story that I'm going to tell today. So I'll start by just defining the notion of Renyi entropies. So let's say X is a random vector in Rd with some density F. Then we have a class of entropies, different measures of sort of amount of randomness in this random variable, so to speak, which are defined in this fashion. I'm going to focus on the continuous case. I won't bother to say differential entropy each time, but that's really what I'm talking about. And there are three special values that are perhaps of most interest, which are the cases when this index p goes to 0, 1, or infinity. When p equals 1, in the limit, we get the Shannon differential entropy, which is just minus the integral of f log f. And when p equals 0, we get the log of the volume of the support of the density. And for p equals infinity, we get the negative logarithm of the maximum of the density. And so these are three different measures of how sort of spread out this distribution is. So I'll start by mentioning two central inequalities. One is the entropy power inequality, which says that, so first of all, we define the entropy power as the exponential of twice the entropy divided by the dimension. The reason for that definition is because if you define it this way, then the entropy power of a Gaussian turns out to be proportional to the variance. And in some sense, when you're doing things with entropy power, usually you're thinking about some Gaussian comparison in the back of your mind. So anyway, so for two independent random vectors, x and y in Rd, it turns out that the entropy power of the sum is super additive. And this is the entropy power inequality, which was first proved by, the first rigorous proof was given by Sc.M in 1959, although Shannon had stated it in his original paper that founded information theory in 1948. And equality holds if and only if x and y are Gaussian with proportional covariance matrices. So there's an analogous, so what's the intuition behind the entropy power inequality? One way to think about it is to draw an analogy with the Brun-Minkowski inequality, which is an inequality in the geometry of sets in Euclidean spaces. So if A and B are Borel sets in Rd, and we write A plus B for the Minkowski sum, that's the set of all vectors x plus y, where x comes from A and y comes from B, and we use modulus for the d-dimensional volume, the Brun-Minkowski inequality says that the volume of A plus B to the 1 over d is super additive. And this is an absolutely foundational inequality for geometry, and it was proved by Brun in 1887 and Minkowski in the 1890s for convex sets, and by Lusternik in 1935 for general Borel sets. And let's note that this can also be written in the sort of entropy form except that the entropy that we are looking at is now the Renyi entropy of order 0, so to speak. So the similarity between these two inequalities, I mean, one instance of why this Brun-Minkowski inequality is important is because it's one way to derive the isoperimetric inequality in Euclidean space, which explains why soap bubbles are spherical, right? The soap bubbles are trying to minimize the surface area subject to a fixed volume of air that's trapped inside the bubble. And so, you know, since it has the capacity to explain that fact, it's clearly fundamental. It's connected to questions of isoperimetry. And similarly, one can think of the entropy power inequality as capturing aspects of isoperimetry in a probabilistic setting. So this similarity between these two inequalities was noticed by Costa and Cover in 1984. And since then, the parallels between these two fields, convex geometry here and information theory here, have been explored in depth. There are 3 surveys on this topic. So as I mentioned, for me personally, the story started with learning about Andrew's central limit theorem, entropic central limit theorem, which Yannis already talked about, so I don't have to give too many details. But this, I should mention, was one of 3 foundational contributions that Andrew made while he was a Ph.D. student. There's the entropic central limit theorem and a definitive form of the Shannon-Macmillan-Bryman theorem, or the asymptotic equipartition property, and his dissertation on logically smooth density estimation, each of which was a sort of landmark contribution in its own right. So the entropic central limit theorem states that if xi are IID random variables with mean 0 and variance 1, and you look at this normalized sum of these IID random variables, then under the minimal condition that this relative entropy from the Gaussian is finite for some m, it has to converge to 0. And as Yannis mentioned, this is equivalent to saying that the entropy of the standardized sum converges to the entropy of the standard normal. And this is very nice because given that the Gaussian distribution has maximum entropy among all densities with mean 0 and variance 1, it suggests an analogy with the second law of thermodynamics, that the central limit theorem is sort of a mathematical second law of thermodynamics, where as you increase the number of summands, the entropy is increasing to the maximum entropy possible. And this limit theorem is intimately connected to the entropy power inequality, which says that the entropy increases at the first step when you go from 1 random variable to 2. And to see that, you can see that if x and y are independent random variables, then this is the entropy power inequality. That reduces to this here because x1 and x2 are now IID. So you just get a factor of 2. And by the scaling property of entropy power, you can put that 2 in the denominator here as a square root of 2. And now you see that this is step 1 in the central limit theorem, and this is step 2 in the central limit theorem. And so this is very suggestive. OK, so there are many questions that one can ask that follow from Andrew's entropic central limit theorem. One is, what refinements of the EPI are available when dealing with more than 2 summands? This is related to the question of monotonicity of entropy in the central limit theorem. Also, we can ask, this is the entropy power inequality that I described holds for independent random variables. What happens if we have dependence? And so these are 2 things I'll talk about. There are many other questions one can ask, which I'm not going to talk about, but I'll briefly mention them here. One is, we can ask if we look at the entropy of linear combinations of IID random variables. So I look at xi IID, and I look at linear combinations, but I take these linear combinations, basically these are with fixed variance. So I'm looking at wi's that sum to 1, so that I have fixed variance. And then you can ask, is the coefficients, when the coefficients are 1 over square root of n, is that the maximal entropy situation or not? And the more general question is whether this should be a psi, this should be a psi as well. Is this psi Schur concave, at least for nice densities f? And this was conjectured by Ball, Nair, and Takoch in 2016, but it turns out to be false even for log concave densities. One can also ask how far the parallelism between information theory and convex geometry go. For example, there are Fisher information inequalities that play a key role in the proof of the entropy power inequality. One can ask, is there a geometric analog of those, which would have to do with surface area, because Fisher information appears as a derivative of entropy, just as surface areas appear as derivatives of volume. And there's an inequality of this type that was conjectured in this influential paper of Dembo, Cover, and Thomas. And it was shown that that conjecture is negative in general by Fradelisi, Giannopoulos, and Mayer. And very recently, we showed that there are actually some positive results for a certain important class of convex bodies. So one can also ask about versions of the EPI for other NE entropies. There's work on that as well, although I won't discuss that either. So, okay, so let me jump into refinements of the entropy power inequality. So I need to define this notion, the notion of a fractional partition. So if we have an index set, which I'll write as square bracket n, this is just 1 up to n, then I can look at a fractional partition as a function on the collection of subsets of this index set such that the sum of these coefficients over all sets that contain any index is 1. Right? So the point to note is that if you insist that this function beta takes only the values 0 and 1, that's exactly the indicator function of a partition of square bracket n. Right? So what this is doing, this is a sort of convex relaxation of the constraint, of the partition constraint. And so these things are called fractional partitions. And an important example of fractional partitions is the case where you have an R-regular hypergraph. That is a collection of subsets of the index set such that for each index, the number of sets that contain it is equal to R. Right? So it's easy to see that if you have an R-regular hypergraph, then you can easily construct a fractional partition here, which turns out to be the indicator function of this R-regular hypergraph divided by this degree R. And so examples of this are the following two fractional partitions. So one is the usual partition into singletons, where your fractional partition beta is just the indicator function of the collection of singletons, and the other is the collection of leave one out sets. Right? So you take all sets of size n minus 1, and you sort of have coefficients that are 1 over n minus 1. So the first theorem I want to mention is that if x1 to xn are independent random vectors, then the entropy power is actually fractionally superadditive. So that means that you have that this is greater than or equal to this linear combination of the entropy powers of the sums, with the coefficients being any fractional partition of the index set. So of course, if you restrict this to the regular notion of partitions, the usual partitions, this is the entropy power inequality. This is the original Shannon-Stam entropy power inequality. The case of the leave one out sets, that's beta n minus 1, was a refinement of the entropy power inequality that was proved by Artstein, Ball, Barth, and Nauer in 2004. And that established the monotonicity of entropy in the central limit theorem. In other words, I mentioned here in Andrew's entropic central limit theorem that you have this convergence of entropies. What Artstein, Ball, Barth, and Nauer showed that not only is there convergence here, but there is also monotonicity. So the entropy is increasing at every step. The increase at from step 1 to 2 was already captured by the EPI, but Artstein, Ball, Barth, and Nauer's result showed that in fact it increases at every step, right? So in any case, various simple proofs of the result of Artstein, Ball, Barth, and Nauer have emerged since then. And in particular, this was the first thing that Andrew and I worked on together. And while we were proving it, we realized that we can extend this to not just to leave one out sets, but we can also prove this for all regular hypergraphs. And we also conjectured there this theorem, and we showed the corresponding Fisher information inequality. But it turned out there were some technical difficulties in proving the full entropy power inequality, which we were able to do with Ghasemi in 2019. Okay, so one can also ask about analogs in the geometric setting of this refinement. And it turns out that an analogous inequality does hold for the volume of Minkowski sum of compact sets in RD. That was proved with Frank Barth very recently. This paper, though, had a gestation period of 14 years, so it wasn't that recent. But nonetheless, it turns out that the natural conjecture here should be that it's not the volume that's fractionally superadditive, but the volume to the 1 over d that's fractionally superadditive, because that's the analog of entropy power. And that conjecture, which was made in another paper with Bobkov and Wang, turns out to be false. There's a counterexample in dimension 12 and above, which we discovered with Fradelisi, Marsiglietti, and Zwavic. And that question is related to interesting questions in geometry, which would be fun to talk about, but not today. Okay, so let me pause here to ask if there are any questions. Okay, so let me proceed to talking about entropy power inequalities for dependent random variables. So for random variables x and y in RD, which are possibly dependent, the question is, can we get meaningful lower bounds on the entropy power of the sum in terms of either the entropy powers of x and y or of related quantities? And there's a history of these things. So in particular, Carlin and Soffer explored CLTs for weakly dependent random variables using entropy methods, but they were not proving entropic convergence, and they didn't have an actual EPI in their paper. The first EPI for dependent random variables was by Takano in the late 90s, but his condition was sort of intricate and not easy to check in examples. Oliver Johnson, who is here, had a paper in 2004 where he proved a Fisher information inequality for dependent random variables and proposed an entropy power inequality involving conditional entropies. So we are going to be inspired by him and prove a result of that nature. In 2011, Olivier Rioul proved dependent entropy power inequality under a condition on the difference of the Fisher information matrices of the random vector. So this is the random vector whose components we are going to sum, and the random vector with the same marginals, but which is a product measure. So the independent version of the independent coupling of those marginals. But he required that assumption not just for the original random vector, but for all of its sort of heat flow evolutes, if you like, or this is something that arises because of the fact that one uses integration along the heat flow, or to relate entropy to Fisher information. In any case, then there was a paper by Howe and Zog in 2018 who proved that for a symmetric random vector, you have this nice inequality. And finally, Arras and Courtade proved in 2022 a lower bound for certain dependent entropy powers, but they were looking at a maximum over a certain class of couplings, and so that's not directly comparable to these other results. So I'm not going to spend too much time on this, but I want to recall that there's a notion of conditional entropy also in the continuous setting, and we can define the important things to remember about the conditional entropy is that they somehow capture the variation of x if you are given y, and the conditional entropy always is smaller than or equal to the unconditional entropy, and with equality if and only if the two random variables are independent. And so we can define a conditional entropy power, which is just the natural thing applied to conditional entropy. And now we can almost state our result, but I need to introduce one more notion, which is the notion of log supermodularity. So we'll say that a function u on Rn, we can take d equals 1 for simplicity here, it doesn't matter. But so a function u on Rn is log supermodular if u of x times u of y is less than or equal to the u of the minimum of x and y times u of the maximum of x and y. And this should hold for all x and y in your vector space. And these are component-wise maxima and minima. So, this might not look very familiar, but actually it comes up in many different situations. This is precisely the sufficient condition in the FKG inequality, which plays an important role in mathematical physics. And this constraint holds for many systems of interest in mathematical physics. For d equals 1, that is real-valued random variables, any density is trivially, or n equals 1, whatever, any density is trivially log supermodular because, of course, 1 of x and y is the minimum, 1 of x and y is the maximum, so that you always have equality here, right, for one in one dimension. So this is really something that only imposes a non-trivial constraint in dimensions bigger than 1. There's a local characterization. So if you have a C2 function, then U is log supermodular if and only if the off-diagonal entries of the Hessian matrix of the logarithm are non-negative. So you can compare this with sort of the local characterization of convexity or concavity, right, which has to do with the positive definiteness of the Hessian matrix. Here, instead of positive definiteness, you have positivity of the off-diagonal entries, right? That's what is key. And so this local characterization implies that a multivariate Gaussian density is log supermodular if and only if the inverse of its covariance matrix has only non-positive off-diagonal entries. These are sometimes called M matrices. So these have been studied, this class of densities has been studied in various classical works going back to, for example, Carlin and Renaud, who observed that log supermodular densities are not closed under convolution. Okay, this turns out to be relevant for us. In contrast, Zartash and Robeva recently, motivated by work on kernel density estimation actually, which connects to other themes of this workshop, conjectured that even though log supermodular densities are not closed under convolution, nonetheless, if you convolve a log supermodular density with a standard Gaussian, it is still log supermodular. Okay, so that brings us to our to this new result with James Melbourne and Cyril Roberto, which says that if you have random vectors in Rd such that their joint density is log supermodular, then you have this conditional sort of entropy power inequality, which says that the entropy power of the sum is greater than or equal to the sum of the conditional entropy powers of each marginal conditioned on all the others. Okay, so for n equals 2, this theorem reduces to this form, where instead of having the entropy power of x and the entropy power of y, we just have these conditional entropy powers. And as I mentioned before, these conditional entropies are always less than or equal to the unconditional entropies. So this gives us a weaker lower bound than what we would have in the independent case, but that's natural. Okay, so in order to prove this theorem, we had to resolve the conjecture of Zartash and Robeva. So we showed that the convolution of any log supermodular density with a product log concave density happens to be log supermodular. And one can also compare our result to the condition of Olivier Riol. His condition was about the difference of these Fisher information matrices being positive semi-definite, whereas our condition boils down to it having non-negative off-diagonal entries. So our theorem also can be compared to the result of Howe and Zog, and it implies a slight weakening of that result, but replacing the assumption of symmetry by the assumption of log supermodularity. Anyway, so okay, so right, so this is all work that directly grew out of out of Andrew's work on entropy power inequalities and so on. Let me mention something that's of a slightly different flavor, but also motivated by similar sort of intuition, and that has to do with other examples of universality in probability theory. So as Yannis mentioned, there are nice ways of understanding not just Gaussian universality, which is the central limit theorem, but also, for example, the convergence to Poisson distributions and so on, using information theory. The original history of of these other examples, all these other examples like convergence to stable laws, convergence to the extreme value distributions, they all go back almost a century, right? So they were all established originally in the first part of the 20th century. In fact, Oliver Johnson, who's here, has, for example, an information theoretic take on some of the extreme value limit theorems and so on. But what is new in terms of universality in general is the Tracy-Widom distributions, which were only discovered in the 1990s. These are distributions on the real line, which turn out to be ubiquitous, but are rather mysterious. There is no explicit description of the densities, not even through the Fourier transform. So unlike the stable laws, where you know the characteristic function, we do not know that for the Tracy-Widom density distributions. They are of enormous importance due to their centrality to what is called the KPZ universality class in mathematical physics. And for example, Martin Heirer won the Fields Medal in 2014, partly for his work connected to this universality class. So where does the Tracy-Widom distribution arise? I'll just look at this TW2. There's a more general parametrized family of Tracy-Widom distributions. So TW2 arises, for example, in random matrix theory. If you take an n by n matrix drawn from the Gaussian unitary ensemble, which, I mean, you can either describe as the probability measure proportional to this, to this quantity, or you can think of in terms of entry-wise having appropriate Gaussian entries, then the largest eigenvalue of this random matrix drawn from this Gaussian unitary ensemble, when you appropriately scale and normalize it, these are not the typical scalings that you find, but when you appropriately scale and normalize it, then you have convergence in distribution to this Tracy-Widom distribution. And this is an extremely important fact that also has many applications to statistics. And for example, I believe Ian Johnstone, who's here, had a package to simulate things about, things related to the Tracy-Widom distributions. They also arise as in taking limits when you're looking at the length of the longest increasing subsequence of a random permutation, for instance, and also for other models. I'm running out of time, so I'll go a bit quicker now. The description, as I said, of the Tracy-Widom distributions is horrendous. Not very transparent, but one can still simulate them and draw pictures. This is a picture from Wikipedia, and one can derive tail asymptotics and so on. But there's not a lot that's qualitatively known about the Tracy-Widom densities. So Percy Deift asked the question of whether these Tracy-Widom densities are log concave, which seems like a natural conjecture when you look at these pictures, and he proved that Tracy-Widom 2 is log concave on the positive real line. This was unpublished, but it's contained in a paper of Bona, Lackner, and Sagan. What we were able to show was that for all beta positive, the Tracy-Widom densities are log concave. And the proof turns out to be very simple, not using the difficult descriptions of the Tracy-Widom densities, but using the Prekopa-Leindler inequality, which is a close cousin to the Brun-Minkowski inequality and the entropy power inequality. I didn't have time to describe it, but what the Prekopa-Leindler inequality gives us is that the pre-limit distributions for a certain model in the Tracy-Widom universality class are log concave, and therefore the limits, which are the Tracy-Widom densities, are also log concave. And in fact, we can also show this for related discrete models. And this gives us a lot of new information about the Tracy-Widom laws, like estimates on the differential entropy, for instance. So let me acknowledge various collaborators whom I mentioned in this talk, starting with Andrew. And in conclusion, let me say that Andrew has been an absolute inspiration for me personally. His dedication to his craft, which anyone who has worked with him knows. Andrew's enthusiasm and energy are boundless. And I have fond memories of Andrew whipping out a pad of paper and starting to write on it. And then suddenly it's 3 hours later and gone through a full pad of paper. And there's no flagging there, right? So thank you, Andrew, for opening so many doors and giving us beautiful things to look at.
And thank you, Mokshay. You know, you've had an enthusiasm for the relationship of the information theory and the probability to various functional inequalities that has really helped this whole program forward. So thank you for that.